We're going to review chapter 5 using the review document and some questions that I picked out. And Tuesday we'll have an exam, but there's no lab. So I'm thinking what I want to do is, if there's enough time after the exam, use some of the lab time to get started with the next chapter. That way, the following Thursday, we won't be so pressured to finish it in the little time we have or run over, whatever the case may be. Okay, so, if you've gone through this chapter 5 review, are there any problems in there that you want to tackle first? Or do you want me to just hit the ground running? Okay. These first ones are pretty much definitions. Gases generally have what? We know that gases have, they're an indefinite shape and an indefinite volume. They also have very low mass for that volume, right? So remember, if you have low mass for a same volume, then the density is going to go down, right? So they have low density as well. So that's the best answer for this one. They don't have closely packed particles. Particles are very far apart. In fact, compared to the size of the molecule of the atom in a gas, the distance between them is huge. It's like planetary distances on a molecular scale. So what's the definition of pressure? Well, basically pressure is a force per unit area. Right? Does that fit with our choices? Defined as the force per unit area is D. That gets you where you want to go. How about the SI unit for pressure? One that we probably won't use very much, but we need to know it anyway. Right? It's the Pascal. So what's the Pascal equal to? It's 1 Newton per square meter. Right? And Newton is a measure of force. What's a Newton equal to? Right, this is not part of the problem, but I'm throwing it in for free. A Newton is based upon Newton's equation, his second law of motion. So if mass, standard mass is the unit of kilogram, and then acceleration is meters per second squared, then Newton would be kilogram meters per second squared per square meter. Right? And the denominator of the numerator is the denominator. So we would have kilograms meters per meter squared second squared. That would cancel out, leave us with 1. So the Pascal is actually 1 kilogram per meter per second squared. Okay, let's make some more room here. Now, why am I concerned with equivalent expressions of units? Because when you put these units into an equation, if you understand how they're constructed, then you may be able to cancel units. But if you don't, if you just put the Pascal in there, try to do a calculation with it, and the answer you're supposed to end up with is something that doesn't come out of the equation itself. That's because you didn't use the equivalent for the Pascal, for instance. Okay, carrying on. A glass column, let me get this out of my way so I can see what I'm doing. A glass column is filled with mercury and inverted in a pool of mercury. Sounds like we're making a barometer. The mercury column stabilizes at a height of 729 millimeters above the pool of mercury. What's the pressure of the atmosphere? All right. 729 millimeters. But oh, okay. So if we've got this barometer in the pool of mercury, and the height from here to this point right here is what, 729 millimeters of mercury. There's a lot of blue smoke in this problem. All it really needed to say was the measurement of atmospheric pressure is 729 millimeters of mercury. What is it in atmospheres? Okay. So 720, we need to convert that to atmospheres, right? And we do it just like we did for the lab. Right? What's the conversion factor? Well, we need millimeters of mercury down here so that this numerator and denominator will cancel. But this is equal to something. It needs to be in atmospheres. So what's the ratio? One atmosphere is 760 millimeters. So divide 760 into 729 and we get something. Right? So it's like, oh, I don't know, 0.8 or 0.9. All right, so C looks like it's the closest one, 0.959. I mean, you'd calculate it. Go ahead. I like to estimate sometimes just to keep my synapses going. All right, let's see, what's next? Oh, I got 6 also. All right, the local weather forecaster reports the current barometric pressure is 30.4 inches of mercury. What's the current pressure in atmospheres? All right, so we did one like this in the lab also. This one just tells you it's 34.4 inches of mercury. We need a conversion factor. Well, we didn't do one exactly like this in the lab because I didn't give you the conversion factor for inches to atmospheres, right? Inches of mercury, let's just do it this way. We need something in inches of mercury that'll convert to atmospheres. Right? Turns out it's 29.92 inches of mercury is 1 atmosphere. So divide 29.92 into that, so it's a little over 1. It's not exactly 1, obviously. A little over 1, 1.02 would be best guess. Okay. We're just doing dimensional analysis all over again. It comes back to haunt you periodically. Air pressure in the inner tube of a tire on a typical racing bike is held at a pressure of 112 psi. That's a lot. Oops. What am I doing? Put the answer there. 112 psi, racing bike. And what you'll notice is on bicycles, as the diameter of the tire decreases, the pressure goes up. The inflation pressure goes up. So I used to have a 10-speed, and I ran it at about 65 psi. And some of these big fat balloon tires, they may be 25 or 30 psi. So 112 psi in atmospheres. What you need is another conversion factor. The one you want to get rid of is on the bottom. The one you want to keep is on the top. So what's the ratio? Oops, sorry. PSI. And I need to read the problem again. Okay, now I'm on track. How many PSI per atmosphere? 14.69 PSI. Divided into 112. So that's in the neighborhood of 7 or 8 atmospheres. I think the pressure is the pressure on your car tires. I think mine's rated at 36 PSI. That's typical. Used to be lower, actually. And it has to do with the construction of the tire, the pressure that will put tread evenly on the ground. If you have too little pressure, then it bulges like this, and you start to get wear on the outside of your tire. And if you put too much pressure, it bulges in the center, and you wear out the center of your tire. Now, any other wear patterns are probably due to alignment. And a skilled technician can tell you what's wrong with your car by just how your tires are wearing. 9. Oh, definitions. What's Boyle's law? Pressure times volume equals a constant. Right? So that would be B. The volume of the fixed amount of gas is inversely proportional to its pressure at constant temperature. That's another way of saying this. And the reason it is because when you have two variables in a, I forgot the term, product, two variables as a product equal a constant, one goes up, the other has to go down. 10, we're talking about Avogadro's law. So Avogadro's law says it's the relationship of moles of gas to volume, and that's equal to a constant. So if we increase the number of moles of gas, we increase the volume. And anytime you specify two variables of a gas equal to something, then the other two have to be constant, P, V, T, and N. So for these two to be variable, temperature and pressure have to be constant. For these two to be variable, temperature and moles have to be constant. Charles' law, that relates what? Volume and temperature. So as temperature goes up, volume goes up. When you have variables in a quotient relationship equal to a constant, they're always directly proportional. Let's see. Next one on my list is 15. Gaseous chlorine is held in two separate containers at identical temperature and pressure. Gaseous chlorine, what would that look like? Held in two vessels. Gaseous chlorine is diatomic. It may not matter to the problem, but it's good to remember. Identical temperature and pressure. The volume of container 1 is 1.3 liters. All right, so I made that one too big. This is volume equals 1.3 liters. And the volume of 2 equals 6.7, excuse me. Oh, and it contains 6.7 moles of gas. So this is 6.70 moles. Those are conditions that are given. The volume of container 2 is 2.33 liters. Okay, how many moles of gas are in 2? So that's the question. All right, so which law would we use? Yeah, before and after, true. And which before and after? Volume and moles. Avogadro. So we've got this N1 over V1 equals N2 over V2. And we can use whatever units are given. Right? The only one we would have to change is temperature. So we're going to solve for N2. N2 equals N1 V2 over V1. Right? I just use a little algebra, solve for the unknown right here. That means V2 comes over to N1 and V1 stays in the denominator. And then we just plug in the numbers. We've done all the thinking part. I'm leaving out the units for convenience. 1.3, and this is 2.33. There you go. $2.33. And then what's the last step after you calculate? 1.20. 1.20 moles is in this one. Now, does that make sense? Well, if we roughly double the volume at the same temperature and pressure, we should roughly, wait a minute, it's not 1.2, it's 12. Yeah, missed my decimal point. It's roughly twice. This is roughly twice, this is roughly twice. So that reality check is what you want to do at the very last step. If I had gotten well, actually, that should have been a signal that something's wrong. It should have been double. So when I saw 1.2, I said, uh-oh. Look at my calculator. Yeah, I missed the decimal point. So decimal had to be moved over one. All right, let's see. Who's next? How about 18? Body temperature is about 309 K. Temperature 309 K. Does that sound right? 273 would be, yeah. Celsius would be 37 degrees. Did you know that? 98.6 Fahrenheit is exactly 37 degrees Celsius. So that's where that number came from. On a cold day, what volume of air at 276 K must a person with a lung capacity of 2.2 liters breathe in to fill the lungs? Okay, so this is the temperature inside the body. All right, let's put temperature inside the body. What's the volume inside the body? Lung capacity of 2.2 liters. So the volume inside the body is 2.2 liters. Okay, temperature outside the body, or the environmental temperature, how about that, is 276 K. We want to know how much of this, what volume of this temperature must we inhale in order to fill that volume at this temperature. Okay, that's what we're asking here. So this is the unknown. And we know that this is a before and after. And what law? Charles, volume temperature, right. So we've got volume of body temperature, body equals volume environment, temperature environment. And we're solving for volume environment. So we say volume body, temperature environment over temperature body equal to V. Okay, who's that? Kaylee. So we would just plug in the numbers now because we've done all the thinking that we need to do. Let's see, volume body, 2.2 liters, 2.20. And the answer is going to be in liters because this one's in liters. That one has to be in liters. And then temperature E276. And then 309. Okay. So this should come out fairly easily. 76 and 309. So I get rounded off, 1.97. 1.97 liters. Okay. That one can be tricky, trying to figure out which one was which. It'd be very methodical about it. Set up our table. All right, 20. Okay. Let's see, you're holding two balloons, an orange balloon and a blue balloon. Okay. The orange balloon is filled with neon. So we got a neon balloon here. I'm not going to draw the balloon yet because they may be different sizes. And then we've got an argon balloon over here. And this is orange, which is probably doesn't matter. And the blue is filled with argon. Okay. The orange balloon has twice the volume of the blue balloon. The orange one is twice as big as the argon. So it's like something like that. So the volume here, the volume of, I'm going to use neon. The volume of the neon is twice the argon. That's the mathematical expression. Okay. Which of the following best represents the mass ratio? Okay. So Avogadro tells us, and we're assuming that all other factors are equal, right? The moles and the volume will change, but the temperature and the pressure have to be the same. And when we say balloon, that usually means that the pressure is the same. And the temperature has to be the same also. If they're in the same room, it probably is. So we're looking for the mass ratio, the mass of neon and the mass of argon. How are they related? Okay, what do we know from this expression? If this one is twice the volume of that one, then the number of moles of neon is equal to twice the number of moles. Needs to be a little end. Twice the number of moles of argon. So this has twice the number of moles. How do we get to mass? Molar mass, right? So for our purposes, since the answers look like they're whole number ratios, so we can estimate. Argon is about 40, right? 40 grams per mole, and neon is about 20 grams per mole. Okay. If neon has twice the number of particles, but weighs half of the mass per particle than argon, then we ought to have the same mass for each one. Right? If this is twice as many, but it weighs half as much, then it should be 1 to 1. Okay. I think in the worked problems, I go into all kinds of algebraic gyrations to prove that. But this explanation is more intuitive, easier to grasp, I think. Let's see. How about this one? 29. I mean, if you like algebraic explanations, then you're welcome to study the review document, worked problems. A gas sample is heated from -20 to 57 degrees C, and a volume increases from 2 liters to 4.5 liters. If the initial pressure is 0.14 atmospheres, what's the final pressure? Okay, so we've got a before and after situation, but we've got multiple factors that are changing, multiple variables. So we need to use the combined gas law. Right? So we're going to have P1 V1 over N1 T1 equals P2 V2 over N2 T2. And are there any of these that we can cancel? A gas sample is heated from such and such, such as the number of moles doesn't change. Right? So what we can do is we can take this factor out. We don't need the moles because it didn't change. So now what we need to do is find out what our values are for, let's see. I'll put P2, V2, and T2 over here. So this is the initial. The gas sample is heated from minus 20 C, minus 20 to what? 57. Okay. And its volume increases from 2 liters to 4.5 liters. How many significant figures here? 3. To 4.5. Okay. Starting pressure. Initial pressure is 0.14 atmospheres. And this is our unknown. What's the ending pressure? Okay. So can we plug numbers in yet? Temperature. Temperature must be converted. We got to add 273 to this, which should be 253 K, and then 273 plus this one be 330 K. Now we can go. We just solved this one for the unknown, which is P2. So P2 equals, and we got P1 V1, and then T2 comes over here. And then V2 goes over here. So T1 V2. That should be correct. Let me check my work. Okay, I'm gonna hold this one here. Yeah. So now you can just plug in the numbers. Right. That's the advantage of setting up a table like this, then solving for the unknown, then plug the numbers in. If you try to do it all in one step, get in a hurry, then there's no telling where your numbers are going to go. But this guarantees that we put them in the right place. So P2 then is going to be 0.14 atmospheres. Is that right? 0.14. Yes, atmospheres. Right there here. And then V1 is 2 liters. And T2 is 330 K. And then T1 is 253. And V2 is 4.5. And we should come up with 0.0811 atmospheres if I did my calculations right. But we can have 3 significant figures. Did that come up? Yep. Okay. Number 30. Let's see, a sample of oxygen gas has a volume of 1.72 liters at 27 degrees and 800 torr. How many oxygen molecules does it contain? All right, before and after or state? Yeah, this is a state because you only have one of each. So if we want to determine the number of molecules, we're going to use the ideal gas equation. PV equals nRT. we're going for N, right? So we need PV and T. And N's going to be our unknown. So what's our pressure? 800 torr. Just a second. I'm going to put this in here with units, because these units are going to tell us what these units need to be. Our pressure needs to be in atmospheres. So what's a torr? I don't know if we talked about that in class. A torr is a millimeter of mercury. Right? So to convert this one to atmospheres, 760 torr is 1 atmosphere. Okay, so that would be our conversion for pressure. How about volume? 1.72 liters. We're good there. That's liters. Temperature, 27 degrees C. Nope. 273 to that one. And that should be 300, right? 300K. Let's go ahead and do that one. 800 divided by 760, so it ought to be greater than 1. 1.053 atmospheres. Okay. Now, if we solve this one for moles, that's not going to go all the way to the answer, but it's going to be pretty close. So solving this one for moles is N equals PV over RT. Right, just take that over here. And setting up our problem, pressure is 1.053 atmospheres. Volume is 1.72 liters. R is 8206. And temperature is 300. So the number of moles would be, see, I already got that one in there, so I'm just going to multiply by 1.72 and 0.08206 divided into it, and 300 divided into that. So I get 7.354 times 10 to the minus 2 moles. And if it wants the number of molecules, now we need to convert that. Moles to molecules. Right? Molecules, yes. Magic number? 6.022 times 10 to the 23rd. Avogadro's number. And let's see, I can round it off to, looks like 3 significant figures. Let's see. That's equal to 4.43 times 10 to the 22nd molecules of O2. And that's A. Okay. So I think the key to this one is deciding whether it's before and after or state. Once you've done that, then you know which formula to go to. Okay. Got lots of repetition there. 37. Let's see. Which conditions of pressure, temperature, and moles, respectively, are most ideal? Pressure, temperature, and mole. Ideal in terms of gas behavior. Right? So we need low pressure, right? High temperature and low moles. These two are kind of joined at the hip, pressure and moles. But low, high, and low looks like E. It's the best answer for that one. You just had to memorize that one, I guess. Now there's a valid reason for it, right? If you're in a hurry on a test, just memorize it. 40. A 41.1 gram sample of neon exerts a certain pressure in a container of fixed volume. What mass of argon is required to exert half the pressure at the same conditions of volume and temperature? Okay, so we got volume and temperature constant. We know that. We've got two containers. One has neon in it and the other has argon. And the relative sizes there are irrelevant because they're fixed anyway. Okay, if we have 41.1 grams of neon, we know that we're going to have, and we want to know, let's see, this is mass of neon. We want to know mass of argon. That will give us the same pressure. In order to exert the same pressure as this, we need the same number of atoms of argon in this one as we do here. All right. Okay, so we can find out how many moles are in here. Well, actually, it's not the same pressure, right? Half pressure. We want the pressure of argon to be half the pressure of neon. So what does that mean in terms of number of particles? We need half the number of atoms of argon as neon. Okay, so how many moles of neon does that represent? Grams, moles, right? We're converting to moles. So neon is 20.18. We're going to keep all of our, we're not going to estimate this one. There's 20.18 divided into 41.1. So that's equal to 2.037 moles of neon. And to exert half the pressure, if this is half the pressure, we want half the number of moles of argon, correct? So I just divide that by 2, and now we have 1.018 moles of argon, and we just convert that back to mass, grams per mole. So argon is 39.95. 39.95 times. And that gives me 4.07. Oops, did it again, 40.7. Sorry, 40.7 grams of argon will do that. Okay. All right, scroll, scroll, scroll. Skip a few, skip a few. For which gas are the molecules diatomic? 49. What we mean by diatomic is 2 atoms, right? Chlorine is diatomic. Right? Helium is monatomic. CH4 is pentatomic. Ammonia is tetratomic. So chlorine is the diatomic one. All right, 52. The mass of 1.12 liters of gas Y at STP is found to be 6.23 grams. The density of gas Y is what? Okay, let's put what we got up here. This gas Y has a volume of 1.12 liters. 1.12 liters. Volume, what's the pressure? Standard pressure is 1 atmosphere. That's what STP means. Standard temperature is 0 degrees Celsius for gases, which is 273 K. Okay, and more mass is 6.23 grams. 6.23 grams. That's everything that's given. We want to figure out the molar mass of gas. No, wait a minute. 52. Sorry, I moved. The density of gas is what? So we want density. Okay. The quickest way to solve this one is to combine equations. We know with these values, we can find out how many moles that gas we have. And with that many moles, we can find out, well, let's see, density is mass per unit volume. We already have the volume. What we need is, wait a minute, that's simpler than I thought. Grams per volume. Oh, okay. The second one is going to be a little more difficult. 6.23 grams per, oh, that's liter. That's fine. The answers are all in grams per liter. 1.12 liters. So what's that? That's about 5.56. Okay. 5.56 grams per liter. And that was the easy one. If we take that same gas, and it looks like 53 is built on the same values, and the molar mass is what we're looking for now. So 53 is looking for molar mass, abbreviated molecular weight. Okay, so that's going to be in terms of what? Mass per mole. We got the mass right here. What we need is the number of moles. So can we get the number of moles from this? Yeah. PV equals N unknown, R known, and T. So if we do this, PV equals nRT, and solve for moles, then we get PV over RT. Right? In molecular weight, then we can substitute this one right here. You could calculate this right here and then put it into the equation. That's fine. But if we're thinking algebraically, we can substitute this expression in for that one right there. And that would give us M over PVRT. And remember, the denominator of the denominator is the numerator. So RT goes up here. Mass RT over PV. So now we can put in the values. 6.23 grams, R 0.08206, temperature 273, and pressure 1 atmosphere, and volume 1.12 liters. And that'll be a direct calculation of the molar mass in one shot. 6.23 0.086273. 1.12 divided. So I get 125. See, yeah, 3 significant foods. Grams per mole.
That ain't close.
Yeah. Okay, so if you feel more comfortable doing this calculation first and then plug that number in here, that's perfectly fine. You know, you'll get the same answer. If working in steps like that keeps your mind from doing backflips. But this way I can, and if I were going to set build an Excel spreadsheet, if I did this calculation, this procedure in the lab over and over and over again, I'd set it up so it would do this. And then I'd have fields in there where I'd put in those values and it would calculate just like that. And it would work on this principle right here. Just practical application. 54, I'm not sure why I left that one blank. It's either a duplicate or it covers material that we haven't looked at yet. So don't worry about 54. It came along after I'd already created the worked problems in longhand, and I didn't feel like going back and renumbering and then doing that all over again. So that was kaput. Uh, 55. Yeah. Okay, 55. Argon has a density of 1.78 grams per liter at STP. How many of the following gases have a density at STP greater than that of argon? All right, let's see. This is what we know. Density of argon is 1.78 grams per liter. Grams per liter at STP. Now, this looks like it's going to be a huge chore. The fact of the matter is, at standard temperature and pressure, these four gases, these other four gases, are going to have exactly the same number of particles, same number of molecules or atoms in that container. So really all you need to do is compare their molar masses, right? The heavier one is going to be denser. The lighter ones are going to be less dense than 1.78. So how many of the following gases have a density that's greater than argon? We just need to compare, let's see, argon, chlorine, helium, ammonia, and nitrogen dioxide. Compare their molar masses. Argon is 3995 grams per mole. Chlorine is 3545 times 2. 70.90. Helium is about 4.00 rounded off. Ammonia, nitrogen is 14.01 and 3 hydrogens is 3.03. 1704. And NO2 is 14.01 for nitrogen, and 2 oxygens is 32. Yep, 32. 4601. 46.01. Now let me go back to my question. What is it asking? How many have a density that's greater than that of argon? So since they have the same number of particles, and each particle weighs different for each one, which one has a higher mass? If it's the same number of particles and the same volume, then all we have to do is compare the masses. So at 39, this one is greater. And this one is greater. Right? So two of them have a greater density at STP than argon. And argon is pretty dense. Right? Of all the noble gases, argon is the one that's most plentiful in our atmosphere. First of all, because it started off more plentiful. And second, because it's so dense that it doesn't float away. Right? Helium and neon are less dense than argon, so they're going to, like that, right out into space. And argon sticks around. Argon is a little less than 1% of our atmosphere. So it's pretty significant. We used to use argon in one of my pieces of equipment, and really all they would have to do is distill air. Right? Just liquefy air and then gradually warm it up and just boil it off. So whatever its boiling point is compared to nitrogen and oxygen primarily, and you can get argon pretty cheap. Now, helium's another story because there's not that much in the atmosphere. I think I told you guys this before. See if you remember. Where do we get helium? Insignificant quantities, enough that we can isolate. Comes out of the ground, dissolved in natural gas. So when natural gas is purified, they take out all the solid particulates and they dry it. They take out the water, and primarily you have methane left, but you've got some helium in there. So they separate the helium, and there are ways to do that. Probably the cheapest way is to use a molecular filter, right? Because CH4 is probably a bigger molecule than helium. So if you try to push it through a filter, the helium is going to go through faster. Right? Like we learned with Graham's law. Helium is going to go through faster, it comes out the other side, and several stages of that, and you got pure helium. Okay, and then you pump it into abandoned salt mines and store it there. Let's see, 56. Okay, 56 might be a little trouble. Which of the following is the best qualitative graph of pressure versus molar mass of a 1 gram sample of different gases at constant volume and temperature? Okay, constant volume, constant temperature, and we want to, let's see, pressure versus molar mass. So we're going to plot pressure versus molar mass. In this case, I would put pressure here. And this is molar mass. Okay, but how are we going to get this value out of a 1 gram sample of different gases? So we have different gases, 1 gram of each, right? 1 gram of different gases, right? Okay, so how is the molecular weight going to relate to that? If we have 1 gram of different gases, yeah, at constant volume and temperature, 1 gram, then the gases, say A, B, and C, or D, these gases are going to have different molar masses. So if they have a different molar mass or a molecular weight, is equal to mass per mole. Okay, they're going to have the same number of moles. No, 1 gram sample will have different numbers of moles because they're different molar masses. Right. So if they're different molar masses, A, and this is 1 gram. So this is going to be different. The number of moles is going to be different. So if we solve for moles and we put, I'm just doing for A, and we can do the same thing for the rest of them. bring that over here, and this is actually 1. That's 1 over molecular weight of A. So how are the number of moles related to molecular weight? Well, if we're gonna plot molecular weight, we actually need to do it the other way. We need molecular weight over here and this over here. Because we want to take the number of moles. So the number of moles of each gas, as the molecular weight increases, the number of moles goes down. They're inversely proportional. So if we have different gases, A, B, C, and D, and say the molecular weight increases as we go, like that, that the molecular weight increase. If the molecular weight is increasing, number of moles is going down. So the number of moles increases going this direction. So if we plot the molecular weight in a linear fashion, the lower molecular weight's down here, which would be the fewer number of moles. So the higher molecular weight would be here. Let's see. Let's do both of them like this. If we were to plot number of moles, what would it look like? Number of moles and pressure. So the number of moles goes up, pressure goes up. Correct? Okay. So if the number of moles is going this direction, how about the molecular weight? If the molecular weight is going that direction, it goes inverse to the number, right? It goes inverse to the number of moles. So it ought to go like that. So as the molecular weight increases, pressure goes down. Okay. Did I lose anybody? So this one is the plot of moles, and this one is the plot of molecular weight. So which one? Oh.
That's why I was confused.
Oh, yeah. Okay. I made an assumption that I shouldn't have.
Would pressure be on the bottom?
Well, it could be. Pressure could be on the bottom. We should get a similar result. Okay, back up. I made an assumption that wasn't actually correct. So the constant here is mass. If mass is constant, equals 1 gram. How are the other two related? Well, molecular weight is grams per mole times moles would be mass. So molecular weight times moles would be that. But how does pressure affect the number of moles? Well, if the pressure goes up, the number of moles has to go up, right? So pressure and moles go up together. So we could write this expression similar to if we don't have to have 1 gram now, but if it's a constant, then our relationship here is like that, equals some constant. If pressure and moles go up together, then they go up together against molecular weight. So as molecular weight goes up, pressure should go down. And that's always a hyperbola. Here. So I had to go around the barn 2 or 3 times to get there, but we're there now. And there are none of those graphs that fit that description. All right. Oh, well, I was close. D shows the right general trend. It's just the wrong shape, right? It is an inverse proportion, but it's not a straight line inverse. It's a hyperbolic inverse. Okay, 58. How are we doing on time? I got 12 minutes. Okay, given reaction, ammonia plus chlorine yields nitrogen gas plus hydrogen chloride gas. You react so much ammonia, 5 liters of chlorine measured at the same conditions in a closed container. What's the ratio of pressures in the container, final versus initial? All right. So if we have this equation, 2NH3 gas plus 3Cl2 gas, and we have N2 gas. Looks like they're all gases. 6HCl gas. Okay. 5 liters of ammonia and 5 liters of chlorine. 5 liters and 5 liters. Same conditions in a closed container. What's the ratio of pressure in the container? Final minus initial, final to initial. So should we expect pressure to go up? Well, we do have two we have two absolute values. And the ratio in moles to moles, since it's all starting at the same pressure, then the ratio of 5 liters to 5 liters, which one's going to run out first? Right. For every 2 of these, we need 3 of those. If we have, if this is 2, then 1 would be 2.5, right? And this one would be 3 would be 5/3. Let's see, 2.5 would be 5/2. So this would be, we'd require more of this one, right? Chlorine should run out. Right, chlorine, this is limiting. All right. Okay, so we know which one is limiting now. This is excess. And we can equate volume to moles because of Avogadro's law. So if we use up all of these, how much of this would we produce? Well, it's 3 to 1. So this would be 5/3, right? We produced a third of what we started with. And this we would produce twice as much. This would be 10 liters. Correct? Right, 3 to 1, 5 to a third of that. And this is twice as much. That would be 10 liters. So now all of this is gone. We used it all up. How much of this is left? Well, if we used up, wait a minute, did I do that right? This is 2. Wait a minute, I might be backwards. Let's see. Let's do it this way. Let's do it the foolproof way. Five liters of ammonia. How much nitrogen can we produce? All right, 1 to 2. All right, so that is 2.5 liters of nitrogen. If we use chlorine, how much nitrogen can we produce? Let's see, 1 nitrogen and 3. So that would be 5/3. So is that less than 2.5? Well, 2.5 would be 5/2. So 5/2 is greater than 5/3, isn't it? 5 divided by 2 is greater than 5 divided by 3. Okay, so I had it backwards. No, I didn't. This produces less, so we're good. right? If I can produce 5/2 from this much, or 5/3 from this much, this is the smaller amount. So this is the limiting one. It produces the smaller amount of nitrogen. Okay, so now I can go back where I was. And this is going to produce 1/3 of 5/3 liter of nitrogen. And since this is the limiting one, 5 is going to produce twice as much hydrogen chloride. So that's how much volume of product we have. And we've used all this up. How much of this did we use up? Well, if we started with 5 liters of chlorine, and we would want to find out how much of ammonia we used up, then this is 3 and this is 2. So 2/3. So 10/3 is how much was required here. 10/3 or 3.33, right? That's how much we use. What do we have left? Well, we have 1.67 liters of ammonia. And we have 1.67 liters of nitrogen. And this is ammonia. And this is hydrogen chloride. Right? So what's the total volume that we have after the reaction? Right? We started off with 10 liters to start with. So we ended up with 10 plus 2, 3.33. And 10. So we ended up with 13.33 liters. Okay, so the ratio of pressure is the same as the ratio of volume. 13.33 divided by 10, which is 1.3. Right? So the answer is C. Do I need to go over that again? Or did you follow me? The only reason that I can do it that way is because of Avogadro's relationship. The number of moles. Remember, you can't move anywhere in an equation unless you know moles, unless you have an equivalent for moles. In this case, volume is our equivalent for moles because everything's gas. So we can ratio volumes just as easily as we can ratio moles. So that's where I went with this, with volume. And the ratio of volume, reactants to, product, product volume of reactants. That's our ratio here, which is equivalent to the ratio of pressure. Okay, and I got 5 minutes. Now, I'm not sure if that's the way I did it in the work problems. It just seemed to flow.
It looks like you did it twice and you marked it out the first time. It looks like that's what you missed it, and then you did it different.
Oh, that turned out to be a better way.
Wait, I think this is 3 times. You did it 3 times.
I did 3 different ways?
I guess so. 58.
Okay. It just goes to show you you can solve a problem in multiple ways. This seems to be the easiest way. 61. When 0.72 grams of a liquid is vaporized at 110 degrees and 0.967 atmospheres, the gas occupies a volume of 0.559 liters. The empirical formula is CH2. What is the molecular formula? All right, remember, work it backwards. If we want to find the molecular formula from the empirical, CH2, we need that multiplier. Okay? So we can know the empirical weight of this one. We can go ahead and calculate that. is 12.01 plus 2.02 for the hydrogens is 14.03. So what we need is a formula that will give us the molecular weight. So how do we get the molecular weight? Molecular weight is mass per moles. Okay. Do we have a mass? Yes. 0.72 grams. 0.72 grams. We need the number of moles. So how do we get the number of moles? We use the ideal gas equation because this is a state function, not before and after. So if we're going to use PV equals nRT, we have to solve for moles. That's PV over RT. We need pressure, volume, and temperature. So what was the pressure? 0.967 atmosphere. Volume, 0.559 liters. So far, our units are compatible with R. Temperature, though, was at 110 degrees Celsius. So we have to add 273 to that. 383 K. Now we can find out the number of moles. So the number of moles is going to be pressure, right? Volume, and R, and T. There we go. Now I could have plugged those back in here and done a single calculation, but I thought I'd do it separate this time. And 0.559. Is that right? Yep. 0.08, 206, and 383. Right. So 1.72 here, 1.72 times 10 to the minus 2 moles, and divide that into 0.72. Then I get 41.9 equals 41.9 grams per mole. Okay. So now what you do is say, if X is 1, 14.03 is the molar mass. That ain't it. If X is 2, it's 28.06. That ain't it. If it's 3, it's about 42. That's probably it. Right? Or you can say ratio. If you ratioed the molecular weight to the empirical weight, that's equal to X. So this is 41.9 divided by 14.03. To the nearest, rounded to the nearest whole number is 3. So 3 times that is C3H6. Okay? Did I lose you again? I'm moving too fast. I ran out of time. How many more do I have to go? Skipped a bunch of it. That's probably why, because I knew I'd run out of time. If you can stick around, we'll do a couple more. I'll at least get it on camera. But if you have other obligations, then I understand. 80. If M is the molar mass, okay, M is the molar mass, and R is the gas constant, T is temperature, P is pressure, which of the following expressions represents the density of a gas? Okay, for this one, we want to combine formulas to find the density. So molar mass is mass per moles. Density equals mass per volume, and let's see, those other values look best as the gas constant there. Okay, so if we solve this one for what factors do we have in common? Well, there's moles and there's moles. So why don't we solve for moles here? PV over RT and substitute that one right here. Okay, solve this one for mass equals density times volume, right? Volume comes over here. Substitute that one for here. That puts density into our formula, which is what we want, right? Because we want to solve the equation such that we can determine density from the other variables. So we got to have density in here somehow, and that's how we get it in here. So this one now becomes D times V, right here. And then this one becomes PV over RT. And then we flip this because the denominator of the denominator is the numerator. So now we have dV RT over PV. Volume cancels. And we're left with dRT over P equals M. But we want to solve it for density. So we leave density here. We bring P over here, M times P, and we bring RT over here. Right? Yep. So MP over RT or PM over RT, A. Yep. How many more do I have? Ooh, I got a few. Okay. Okay. I'm gonna keep rolling.
Good.
Yeah. Let's see. All I have at 2:30 is office hours, and that doesn't matter. 81. One way to isolate metals from their ores is to react metal oxide with carbon in this reaction. So if we have 2 times the metal oxide, and this only works for one oxygen and one metal. Right? But if you have different metals, different combinations of oxygen, you can get a particular reaction that's valid for that metal. But this one works for a single metal and a single oxygen in the molecule. Okay, so if we have 34.08 grams of metal oxide, 34.08 grams metal oxide, excess carbon, which is reasonable. That's the way they do it. And 4.37 liters of CO2 is formed. 4.37 liters of CO2 is formed at 100 degrees and 1.50 atmospheres. What's the identity of the metal? Okay. How do we tell the identity of an element? There are only 2 ways. If you know the Z number or the atomic number, right? It's easy to find. But if you don't have access to that, and I don't think we can get it from this value, then you go for molar mass. If you can find the molar mass, then you can get pretty close. The molar mass gets bigger from top to bottom, left to right. So you do the same thing with it that you do with atomic number. So how are we going to get molar mass out of this? Well, we need mass per mole. We got the mass. We got the mass of MO. We need the mass here. Right? We need the number of grams there. Okay. So, Let's see, did I miss anything? 34.08 grams of metal oxide react with excess carbon. Okay. So what we've got to do is find two values, the mass here and the moles here. We can easily find the moles because we can use this in the ideal gas equation to find the moles of that and convert this. Right? So PV equals nRT. Let me just do it this way. Then solve for moles, which would be PV over RT. This has to be plus 273 equals 373. Okay. Atmospheres, liters, that's good. So pressure is 1.5 atmospheres, volume is 4.37 liters. R is the same one as always. And temperature is 373. So we can find the number of moles of CO2, 4.5 and 4.37, 0.08206 divided 373 divided. So this is 0.21416 moles of CO2. So if the ratio is 1 to 2, for every one of these, you had two of those. So the moles of M would be twice that, or 0.4283 moles of M. So we got moles. Now we need to figure out mass. Okay. We know the ratio here is 1 mole of M to 1 mole of oxygen. How many moles of oxygen did we produce over here? Well, if we have this many moles of CO2, we produce twice as many moles, or that many moles of oxygen. Right? So we consumed 0.4283 moles of oxygen, correct? Okay. So what does that represent in terms of mass? Moles cancel, leaves us with mass, 16 at that. So that's 6.853 grams of oxygen. So grams of oxygen subtracted from total mass should be what's the mass of M? Minus 6.853. So I'm just going to change the sign here and add 34.08. So that's 27.23 grams of M. Now we have mass. And we have moles. Okay. So 27.23 divided by 0.04283. Oops. Try that again. 0.4283 is 63.6 grams per mole. Now we can look. That's copper. Did I lose anybody? Because I moved pretty quick on that one. The key here is to know what it takes to get the molecular weight. We need mass and moles. Moles was easy because we have this information. Mass was a little tricky. We knew the mass of this one. We had to figure out what's the mass of oxygen in order to subtract it and get the mass that's left over. So that's where knowing that we have the same number of moles of oxygen as, say it's 2 here, 2 here, same number of moles of oxygen as to do the metal. And then relating that to this, because if we have the same number of moles as the metal, then we can say, all right, I know the number of moles of oxygen is equal to the metal, so I can just subtract the whole number of oxygen from that value once I find the mass. Okay, 82. Definitions. Standard temperature for gas. 0 degrees C. Standard pressure for gas. 1 atmosphere. How many more of these things do we have? A bunch. Let's see. That's 1, 2, 3, 4, 5, 6, 7. Some of those are memorization. 9, 10, 11, 12, 15. I may have to be selective about the rest of them. Okay, where was I? It's past 83. Should be this one. A 142 mil sample of gas is collected over water. What's the volume? Okay, this one requires more than one law. I probably ought to do this one. Get it on video. This one is one where drawing a picture would help. Gas collected over water. Okay, so typically what you have here is an inverted, some sort of a measuring device like a graduated cylinder. Then you have water. And you have a reaction vessel that delivers the gas here. So it bubbles up here and produces a certain volume. And this is your reaction vessel to produce the gas. Okay, we're collecting this gas over water, and we find that it's 142 milliliters here. 142 milliliters. What's in that? What's in that 142 milliliters is a combination of the gas plus water vapor. And so we got two gases in there. That means Dalton's law of partial pressures is probably going to come into play. Okay. 22 degrees C and 753 torr. So the temperature here is 22 degrees C and 753 millimeters of mercury or torr. Okay. Pressure, temperature. Okay. We want to know what the volume of the dry gas is at standard temperature and pressure. So the vapor pressure of water at 22 degrees is 20 torr. That means this total pressure in here, here's the total pressure. Total pressure is equal to the pressure of the gas plus the pressure of water. So if we subtract water from that one, right, 753 minus 20 torr for the water, so that's 733 torr of dry gas. We just took out the water vapor. What's the volume of the dry gas at STP? Well, that's 733 torr. Pressure would be 733 divided by 760 would be the pressure in atmospheres. Oops, yes. 0.964 atmospheres. Temperature equals 22 plus 273 or 293 K. And you know what? I think this is a before and after. What is the volume? Oh. I'm making it harder than it needs to be. Pressure and volume are related as long as we don't change the temperature and, well, the moles are going to change, but the relationship between volume and pressure is linear. In other words, we subtracted 20, let's see, 20. The mole fraction of the dry gas is the ratio of pressure, its pressure to the final pressure. That's the fraction of the volume. 733 divided by 753 is 0.973 is the mole fraction of the dry gas. So that ratio is going to be the same for the volume. So 142 times 0.973 should be the volume that's left over for the dry gas. Times 138. Right? Well, yeah, none of these. Right? 136 is close, but it's not exact. Right? 138 is the correct value. 136 is close, but no cigar. Does that make sense? Okay. Let's see. I'm gonna skip 88. If you really want 88, you can look at a previous video that I'm sure is in there. Or keep note of the ones I skipped and just splice them in there from a previous video. You know, maybe that's what I ought to do. Starting with 88. Let's see what the other numbers are. 94, 95. That's what I'm going to do rather than keep you guys around. 96. 103. 109, 111. And any more? 16, 17, 18. Okay. And 124. 132. 'That's it. So I'll go to a previously recorded video and I'll pull these out and splice them on the end of today's video. 88. Oxygen gas generated by the reaction 2-KClO3, potassium chlorate yields potassium chloride plus oxygen. gas. These are both solids. Okay, it's collected over water at 27 degrees in 1.55 liter vessel at a total pressure of 1 atmosphere. Okay, so again, we've got this over water. We got a vessel of some kind, and we're collecting the gas from our reaction. This has potassium chlorate in it, and it's generating oxygen gas. Okay. 27 degrees. It's the temperature, 1.55 liter vessel at a total pressure of 1 atmosphere. So it's 1 atmosphere pressure and 1.55 liters is the volume. The vapor pressure of water at 27 is 26 torr. So pressure of water equals 26 torr at this temperature, 27 degrees C. Okay, that's everything that's given. How many moles of KCl3 were consumed in the reaction? What we need to do is find out how many moles of oxygen are there. Well, if the pressure is 1 atmosphere or 760 torr is total, then the pressure of oxygen in that container has to add to it 26. So the pressure of O2 is equal to 760 minus 26. Be sure I get my numbers right. Minus 26 torr, yes. Okay, so that's 4 and 2 from 5 is 3, 730 torr. Well, we're going to need this in atmospheres because we're going to use PV in RT to find out how many moles. So we just divide this by 760. And that's the case. Calculator. 734, 760 is 0.9658 atmospheres. So we need that value. We need this temperature plus 273 equals 300 K. Need that temperature. We've got pressure, temperature, volume. Now we can calculate moles of oxygen produced. So the pressure in atmospheres is 0.9658. Volume is 1.55. R is 0.08206. And T is 300. Okay, so that'll give us the moles of oxygen. Let's see, 1.55 and 0.08206, 300. So that's 6.08 times 10 to the minus 2 moles of oxygen produced. The question is, how many moles of KClO3 were consumed? Now it's just a simple matter of unit conversion. O2 versus KClO3. Well, the ratio is 3 to 2. So 2/3 of that value is 4.05 times 10 to the minus 2 moles. Oh, standard notation. Okay, let's put some zeros out here. Move it 2 places. 1, 2. 0.0405 moles. That's C. Okay. All righty then. 88. Who's next? How about this one? There we go. That's good. 94. So we've got a 3-liter bulb and a 2-liter bulb. 3-liter bulb connected by a valve with a 2-liter bulb. Okay. Let's see, we got extra zeros in there. There we go. A 2-liter bulb in which the gas pressure is 1.8 atmospheres. 2-liter is 1.8 atmospheres. Okay. And a 3-liter bulb in which the gas pressure is 3 atmospheres. All right. What's the final pressure in the 2 bulbs? Temperature remains constant. So this problem requires that we think abstractly. In other words, we solve the problem by finding out what's the pressure in the system if there's nothing here on this side. It's a vacuum. And then we go and say, what would happen though if this were a vacuum? And we open the valve. And we get a contribution of pressure in the whole thing from this side and a contribution from that side. And then we use Dalton's law to add them together and find the total. So we need pressure volume. Let's see. Let's say this is 1 and this is 2. So P1 V1 equals P2 V2. Well, for this side, we're going to say that one's 0. It still has 2-liter volume, but there's no pressure in it. Right? So this is going to be pressure 1 is 3 liters, 3 atmospheres. Volume 1 is 3 liters. Pressure 2 is unknown. Volume 2 is what? Well, once we open that valve to this side, and that's a vacuum, then we're using 3 liters and 2 liters. So this is 5 liters. So P2 equals 3 times 3 is 9 minus 5. Equals the pressure. 1.8 atmospheres. Okay. That's if we go from this side. If we go from this side, now the beginning pressure is 1.8 atmospheres. And the beginning volume is 2 liters. This again is the pressure if that's a vacuum. And the final volume is still 5 liters. Okay. So if we multiply these two together, we get to 3.6 divided by 5. Right? Is 0.72. So P2 equals 0.72. The total pressure is equal to pressure from number 1 in a vacuum plus number 2 in a vacuum. So the total pressure is 1.80 plus 0.72, which is 2.52 atmosphere. Okay, that's C. Okay, scroll down to 95. The partial pressures of methane, nitrogen, and oxygen in a sample of gas were found to be 135, 508, and 571 respectively. Calculate the mole fraction of nitrogen. All right. One thing we've learned is that the mole fraction of any gas, in this case nitrogen, is proportional to the pressure fraction, pressure of nitrogen over the total pressure. Actually, it's exactly equal to that. All other factors being equal, the pressure of nitrogen in that container is proportional to the moles. So we ratio the pressure to the total pressure, we get the mole fraction. So nitrogen is the second one, 508. And then the total is 508 plus 135 plus 571. That should give us the mole fraction of nitrogen. 508. And then 135 and 571 and divide. So I get 0.418. C, that's the mole fraction. And that's a dimensionless number, right? Because millimeters of mercury on the top and the bottom cancel. Right? It has no dimensions, which can be dangerous unless you know exactly where it came from. If we identify that as the mole fraction, then we know that this is applied to nitrogen versus the total. Dalton's law of partial pressures, just memorize the definition. That's the total pressure of mixed of gases is the sum of the partial pressures of all the gases. And then there we go. We got another one. 103. Calculate the root mean square velocity for O2 molecules in a sample of O2 gas at 11.8 degrees C. All right, go to your useful information and you'll get the root mean square velocity. Mean square. I think they use a U. Is equal to the square root of let's see. I have to look it up myself. Um, 3RT over 3 times R times temperature over the molar mass. I'll say molecular weight, molar mass. Okay. The trick to this one is be sure and use the right units of measure here. Because if we've got a square root of 3 times 8.3145, this is joules per mole K. And joules is based upon international standard units, kilograms. That means the molar mass and the temperature, of course, which would be, let's see, what was the temperature? 11.8 C. 11.8 plus 273. Okay. Divided by the molar mass has to be converted to not grams per mole, but kilograms per mole. So oxygen O2 would be 32 grams per mole. And I just say if we're going to convert it to kilograms, we have to say 32 times 10 to the minus 3 kilograms per mole. Because that's 1,000. A gram is 1,000th of a kilogram. So that's what this term is for right here. All right, this goes in here. 3. And notice I don't have to put it in scientific notation because my calculator will accept exponential notation like that. So let's say 3 enter 8.3145 times and 11.8 plus 273 times, and then divide by 32 exponent minus 3. So the velocity, the root mean square velocity of oxygen under those conditions is 2.22 times 10 to the 5th meters per second. If I did that right. I got 471. Okay, I did something wrong. Let me see what it is. Oxygen gas, 3RT. Okay, divided by molar mass. Molar mass is 32. So this should be yeah, that's right. Kilogram would be 1,000 times that. That would drop out 32. Okay. Let's see. Did I do the calculation correct? Oh, I forgot one important step. The square root. So let me take the square root here. Okay. Square root of that. That equals 4.71 times 10 squared, or 471 meters per second. Details. Details matter. C is the answer. Okay, 109. Which of the following is included as a postulate in the kinetic molecular theory of ideal gas? Well, let's see. The distance between gas molecules is small compared to the size of the molecule. That's false, right? A is false. The distance between molecules is huge compared to the size of the molecule. B, all collisions between molecules are elastic. What does that mean? We didn't use that term in the lecture. Elastic means conservation of energy. In other words, there's no energy lost in the impact. Or as they come together, bounce off, they got the same energy going as coming. So B is correct. 100% elastic collisions. And C, in an average collision between molecules, both molecules have the same kinetic energy. No, they don't. They don't have to. They can be traveling at the same velocity, but they might have different energies because they're different sizes. Right? So C is false. D, all the molecules are move randomly in zigzag directions. Okay, if they'd have stopped it randomly, it would have been correct. But zigzag, there's no way to tell, right? It could travel in a straight line and bounce straight back, right? That's not zigzag. So all you need to do, all you have to do to disqualify a statement is to find one exception, and we found one exception. So D is false. All molecules have the same velocity. Nope. Now, hold on a second. If the temperature is a measure of the average kinetic energy of all the molecules in a container. So if we take the temperature of the container before it reacts, then all the molecules will have the same average kinetic energy. Okay. In an average collision between molecules, I'm looking at C again. Both molecules have the same kinetic energy. No, they have a distribution of energies. So if this is the energy scale, and this is the number of molecules, then they would generally have a shape like this. Most of them would be in this range, but they wouldn't be the same. Some of them would be out here, some of them would be over here. So that's the key to C being false, is the same kinetic energy. No, they have the same average kinetic energy for the whole group, right? But they don't have the exact same energy. Both molecules don't have the same energy. All right, so we were correct initially. B is the only correct one in there without any qualifications. Let's see, 111, Graham's law. All right, let's see, I think there's a mathematical expression for Graham's law, which is let's see, what did I mean by that? ER, energy of, I think it's distance traveled. ER A. So I'm going to say distance for molecule A related to distance for molecule B is proportional to the square root of the molecular weight of B divided by the molecular weight of A. So they're inversely, this ratio is inversely proportional to the square root of the molar masses. Yeah. Okay, I know what ER means. ER for A, ER for B. In your useful information, that means effusion rate. So the rate for A compared to the rate for B of movement of the molecules. So if you measure the distance traveled over the same time interval for both of them, then the time interval drops out, and now you're talking about distance. But the exact value is the rates of effusion of gases are inversely proportional to the square roots of their molar masses. That's what this says right here, here and here. That's Graham's law. 116. Hydrogen and chlorine gases react to form hydrogen chloride. You and a friend on opposite sides of a long hallway, you have the hydrogen and your friend has the chlorine. You both want to form hydrogen chloride in the middle of the room. Which of the following is true? So we look at our choices. When do you release the gases? All right. Well, Graham's law says that hydrogen gas will move faster than chlorine gas because of the mass difference. This is 2.02 grams per mole. This is 70 point, let's see, 35, 45, 90 grams per mole. So if the hydrogen is going to move faster, this is your long hallway, right? And let's see, who's who? I've got the hydrogen, so this is me. I've got the hydrogen. And this is my friend who's got the chlorine. Okay, we want them to meet right in the middle. Okay, so which one releases first? The one that moves the slowest has to release first so that it has time to get to the middle before the hydrogen does, or at the same time the hydrogen does. So this is release early, and this is release late. Chlorine has to be released first because it moves slower, according to Graham's law. So B, your friend should release chlorine first. That's the one. Okay. How about 117? Order the following in increasing rate of effusion. So we want to order them by which one goes fastest. Oh, increasing rate. Which one's slowest to the fastest. So since they're inversely proportional to their molar mass, the slowest one is going to be the heaviest one. So what we need to do is find out which one that is. F2, Cl2, NO2, I think, and CH4. So the molar mass of this one is 38 grams per mole because it's 19 for each one. And this one I just did 35, 70, 45, 90 grams per mole. NO is 14.01 and 16. So that's 30.01. And this one adds another oxygen on it. So it's 46.01. And this one is 12.01 plus 4.04 for the hydrogens, 16.05. Okay, from slowest to fastest, increasing rate. So the rate increases as you decrease the molar mass. Okay, what's the smallest one? 16.05 ought to be over here. Well, let's put that's methane. Methane is the fastest in terms of rate. Okay, the slowest one is going to be chlorine. Okay, then the next one is going to be NO2. Okay, we got this one, we got this one, we got this one, then F2, and then NO. Okay, so let's see which one matches that. Chlorine, NO2, fluorine, NO. A would be your answer. $118. This thing's getting kind of light. Complete the following. Because real gas particles have attraction for one another, let's see. A, real gases act most ideally at standard temperature and pressure. No, because that implies that once you've reached standard temperature and pressure, you have ideal behavior, and anything outside those values is non-ideal. So that's not right. B, we assume gas particles have negligible zero volume. Well, let's look at the statement. Because real gases have attraction for one another, we don't assume anything about their volume according to attraction. What we want to see for attraction purposes is energies. So C also says 1 mole of an ideal gas at volume at standard temperature and pressure has a volume of 22.4 liters. That has nothing to do with attraction. D, real gases act more ideally at higher temperatures and lower pressures. That's the one that overcomes attractions, high temperatures and low pressures. So D is the correct answer. (124). Of the following real gases, which would be expected to have the lowest van der Waals correction for intermolecular attractions? All right, we want gases that do not attract. Lowest van der Waals correction for intermolecular attraction. One thing we have to have is nonpolar behavior. And the other we have to have is small size. The smaller the size of the molecule, the greater the distance between molecules, plus at any given temperature, the higher the velocity. So what we want is something that's small and nonpolar. Ammonia can't be it, because ammonia is like this, right? It has this pyramidal shape, and it's polar. Right, so ammonia has very strong attractions to one another. Hydrogen, chlorine, and oxygen are all nonpolar because they're bound together, equal elements, and they share electrons equally. So there's no polar nature to any of those. What we'd see, though, is with the smaller one, you have less possibility for attractive forces because it's concentrated in a small area, and when they get close to one another, well, this is a topic we need to hold this topic till later. So just memorize the answer for this one. The attraction is based upon size. So if we have a large molecule or a large atom, the likelihood that the electrons are going to congregate on one side or the other, more often producing a slight imbalance of charge, is more likely. So the larger one, the chlorine, is a huge molecule compared to oxygen, which is also huge compared to hydrogen. The least attractive forces will be experienced by hydrogen. All right, 132. That's not working either. A manometer is attached to a sample of gas that occupies a volume of 2.34 liters. The mercury level in the arm of the manometer attached to the gas sample is 24.3 torr, lower than that of the arm open to the atmosphere. Okay, this tells us how the picture should be drawn. Manometer is a pressure measuring device for trapped gases. So if we have a gas trapped here, and we attach it to a manometer, and that's open to the atmosphere, okay? Then we're told that the volume is 2.34 liters. Well, maybe we need that, maybe we don't. The arm of the manometer attached to the gas sample on this side is 24.3 torr lower than the arm on this side. So if we have mercury this side, then the difference between the two is 24.3 torr. Okay. The atmospheric pressure is 1.23 atmospheres. That's pretty high, actually. 1.23 atmosphere. Okay. So what's the pressure of the gas, the sample of gas here? Well, it's obviously enough pressure to hold this much mercury up, plus the pressure of the external atmosphere. So the pressure inside here is equal to this pressure plus that pressure. So 24.3 torr. Let's see, our answers are in torr. 24.3 torr plus this is 760 torr per atmosphere. So we multiply 1.23 times 760 is 935 plus 900, let's see, we already got that, 35 torr, and it's 24.3 is about 959 torr. Got anything close to that? Yeah, E, 959 torr. This is the tricky part right in here, understanding how that's set up. That's why drawing a picture is often helpful.